Ready? Ready on the left? You guys ready? Ready on the right? All right. Who's it going to be? Last name's Q through Z. Bring them on down to the front.
That's why I was so concerned. I didn't have a feeling.
You just had a feeling? All right. All right. Here we go. Stack them right here. Add them to the pile. Let it stack right here. All right. Good. Very good.
Question, do you guys have the homework yesterday?
I do. Maybe a break or after
Okay,
class.
break's fine.
Okay. Done. All right. Very good. Daija, I have homework from you. I think I have 2 homeworks actually. So, catch you at the break or after class.
Okay.
I got it. They're all over here. So, just throw it in here. At the break. There we go. Q through Z. There's only one Q.
Well, you mean, I'm not sure today, but I just have a question for this thing. I thought that this was I heard in class you kept saying 5, so I
Yeah, we have to push it up to 5 to get a single, to get to the units level of meters per second. If I said to the nearest 10 meters per second, then it would have been. But it's good. Thank you. Anybody else? Speak now or forever hold your peace. Q through Z. What was that? You just went like this. Was that? Were you giving him a slap? Oh, okay. All right. So Q through Z, homework. Is your last name Q through Z? Okay, good. It's good. It's neutral, actually. Okay, everybody else to the aisle, and somebody at the aisle, bring it on down here to the front. This is for Daniel's pile. So that's A through P. A through Papa. Send it to the aisle. Patrick, it's all right. You don't have to collect it. Just let everybody else bring it up. That's fine. You just take care of your row. Everything's fine. Just set it right here. This is the big pile. Here's the big pile, the Daniel Reinhardt pile. Very good, thank you. All right, very good, nice. Okay. All right, thank you. Okay, thank you. What's your last name? Put it in the pile here. Okay. I'm over here. Okay. I saw you spit. Okay, great. Thanks, Frank. Let's go. One more pile for Daniel. Thank you. Okay. No rush. Everything's good. One more. Up. Now you're good. Jalen Rose, are you here? Did you get my message? Talk to me after class. We're looking good. Oh my goodness. Poor Daniel. Okay, couple things I want to mention to you with regard, well, we'll talk about the homework. Previous homework, if you weren't here yesterday when we handed back homework 2, the big pile, I have them up here. You can catch me either at break or at the end of class, and hopefully we'll have a few minutes to grab homework if you weren't here. Another thing, I'm going to give you a Wiley Plus homework over the weekend from chapter 22, which we're going to be talking about a little bit more today in detail. And then Monday we'll probably finish 22 and do a little bit of 23 and then a little bit of 23 before class on Tuesday, or at the beginning of class Tuesday. And then have a chapter 21, 22, 23 exam. 23 will be pretty basic. It's AC circuits, so we're not going to get bodacious with that. However, also, somebody pointed out in discussions yesterday that actually we have a little bit of chapter 20 on this next exam, the exponential decay of the RC circuit. Okay, because we did that on Monday. So I think it's like the last section but one of chapter 20. It's pretty, it's the RC circuit. And I want to give you this piece of mental guidance or mental advice that the stuff that we talked about today is oriented to circuits, and the main, I mean, there's a lot of reasons to talk about electromagnetic induction for an astrophysicist, for instance. But for us, I'm going to orient it mainly to circuits, and so just a sneak preview of your mental outlook. And also, chapter 3 is AC circuits. That's what it's about. So I'm streamlining our concepts down to those that meet with circuitry, and you have an AC circuits lab coming up. In your labs. So now let's talk about this separation of isotopes. What you did was basically the Calutron exercise, various designs. We did a quarter turn. If you did a full 180-degree turn, the way some machines are, it'd be a little bit different calculation. So I, made a really precise diagram. And I saw a couple people with diagrams that were looking a little bit shaky, but we're going to let the numbers do the talk. I mean, it can't be like a triangle or something. I mean, it's got to look a little bit circular. But we're going to let the numbers do the talking, all right? Your diagram will be graded, but if the numbers do the talking, I'm going to overlook a lot in your diagram if it's, if it's not too bodaciously wrong. All right, so for the light potassium ion, potassium 39, you were to calculate its outlet speed from the parallel plates, and then calculate its radius of curvature, and therefore figure out its landing point up here in this bucket. And then we were to figure out the landing point of the heavy ions, which were above that. Oh, let me do a clicker question with you. Raise your, okay, and it's going to be, boy. I know I asked you for, to the nearest 0.001 meters. And so what I want you to do is try to enter your result just so I can see who's got what. So go ahead, get a Go Nitro, and then type in the number for your separation, your final number. All right? Capital D. And type a 0 first, and then a decimal point. And I have to apologize. The decimal point is really hard to locate. You need a microscope to see it. But type in a 0 first, and then do the decimal point, and then the rest of your numbers. For D, not for the radii, but for D, capital D. And just do that right now, just so I have a tally of who's got what. Let me see what you guys are voting for here. Oh my goodness. Oh my gracious. We have a lot of people absolutely blazing here. All right. Just type in your, and then hit the send key. Always hit the send key, and that'll be good. Oh my gracious. All right, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, 192 people. That's not bad. You guys did good, looks like. Okay, so the other thing was to calculate the same two quantities, the exit velocity and the radius for the heavy potassium 41. And potassium 41 is a few percent in nature. Most potassium that you find is potassium 39, the light one. But I'm guessing that researchers use this pair of ions to track things across cell membranes and stuff. You know, the sodium-potassium business, the bilipid layers and all that. So this is actually good that you have looked at it a little bit. Now the thing is to figure out the difference in the landing points. You want to kind of graph these up on the same on the same thing, but they're so close together in this scale that I couldn't really do it. Anybody remember having that pair of numbers? I saw a bunch of you when you turned it in, so that's good. The answer, the bottom line answer is, so we're going to be looking at your velocities. We're going to be looking at your R's, and then we're going to be looking at your, basically the difference of those two. But I can't graph it up on this because that is in proportional to, 402 millimeters. That's 10 millimeters up there. So it's kind of hard to, excuse me, it's kind of hard to show both of these trajectories next to each other. They just kind of merge together at this scale. Anyways, I saw a bunch of those, so you're looking very good with that. All right. Now, we don't have, before the exam, we were talking in office hours yesterday, and I was, we were talking to the students about the homework that they had prior to exam 1, the written homework that was due that day, and then electric field extra practice or extra practice with electric fields in web courses. And the exam was heavy on those two. And then calculation-wise, concept-wise, it was, it was kind of a smorgasbord. But calculation-wise, it was. So I want you to keep that in mind as you prepare for exam 2. We've had this homework. We're going to have another homework. I don't think I'll put any homework in web courses about what we do today. But I will, by lunchtime tomorrow, have a Wiley Plus assignment about magnetic fields and circuit elements that we talk about today. All right. Now, this homework was a good homework to prepare for exam 2. All right. I'll just put it that way. That is not a hint. But having done this homework, and a lot of you, it looks like you did it well, that'll help you to, with what you do find on exam 2, at least part of what you find on exam 2, you'll be happier for having done that. Now, questions from the floor? Yes? What I'll do is probably put up a few problems that I like. That list is pretty short. I usually have a little bit more on that list. And I put some up earlier this week on the problems that I like list. And I think I might do that. And what I'm going to do is try to find ones that you guys have in the Student Solutions Manual. Does anybody not have access to the Student Solutions Manual? I mean, it's kind of okay. The Student Solutions Manual is whatever it is. I don't know. I haven't even seen it. The other thing that we can do is sometimes I just like the examples in the book. Like the ones that we did Monday were from the book. So it just depends. All right. Now, I want to talk about this image, figure 2130 from chapter 21. And I want you to look at it carefully. If you start current moving around in that loop, it's as if you've placed a magnet, a bar magnet, in the loop, because you get a dipole field. And here's the field. It's shaped a lot like this. Okay? And depending on the diameter of the loop and how much current you got, you'll have so many field lines, but it'll be some kind of a dipole shape. Right? And here's the right-hand rule for the direction of the current and the central field in the loop. Use the right-hand rule. And the textbook says use your thumb for the currents, and then in the center of the loop. Oh my goodness, I forgot to give you guys a right hand. We're going to have like Monday is going to have to be right hand rule revenge day, because you guys need more practice with that. No, because I don't have the clicker. I don't have any right hand rule clicker questions set up. So I'll do a couple, 3 good right-hand rule you know. So be ready. Anyways, now here's a question. You know, you get the current moving, and it's like it makes a magnetic field, almost like a bar magnet field. And you can get other shapes of magnetic fields and stuff, but this is a simple example. So a logical question might be this one. Go ahead and write this one down in your notes. Is the opposite possible? Can you create current by putting a magnet in the loop? What we did was we took current and we made a magnet out of it. So the question is, can you take a magnet and make current out of it? You know, with the right size wire and stuff like that. All right, now here's another way to state this. And this is kind of a semi-quote from Michael Faraday. Here's a picture of Michael Faraday when he was young. Is it possible to produce electricity from ordinary magnetism? See, he was convinced, and many people were convinced in the early 1800s that once they found that a magnetic field was set up by a current-carrying wire, Christian Ørsted did that. You know, that's a guy that was getting ready for lecture, and he turned on the current, and his compass needles went haywire. Once they discovered that and they started working on it, they were convinced that magnetism and electricity, heretofore unrelated, were actually related. And Michael Faraday was also working on that as well at that time. He was convinced that they were, most people were convinced, whereas 50 years earlier than that, maybe not. Not many people had a clue about it. So it was interesting for me to go back and look at you can actually look at his notebooks. They still keep all of Michael Faraday's experimental equipment, or most of it, from 150 years ago, because it's so profound, the things that he figured out, the theories that he developed. But this is like the overarching question of his whole scientific career. You know, the relationship between electricity and magnetism. And my wonderful students, you may have heard this phrase, unified field theory. And that is a phrase that I first heard when I was a kid. My uncle is a physicist, and he's passed away now. But I remember my uncle and my dad. My dad was a lawyer, so he, lawyers, they have to get their mind halfway around any topic. So he loved talking with my uncle about physics. And I remember when I was a little kid, like in third grade or something, hearing them talk about Einstein. And see, I grew up in New Jersey, and that's where Einstein lived, down in Princeton. And he had been dead for a number of years, but everybody still talked about him. And I remember, listening to my uncle, my dad talk about the unified field theory. And that's what Einstein was trying to figure out. He was trying to unify electromagnetism and gravitation and wasn't able to do so. The first unified field theory was actually this, and the guy that unified it was Michael Faraday. And now I'll also tell you of the four forces in nature. There's four forces in nature. There's the electromagnetic interaction, which used to be two forces, electricity and magnetism, but now we know that they're just one. And then there's gravitation, Newton's law of universal gravitation. And then there's two nuclear forces that are very short range, but we have discovered that they're distinct forces, and they're involved with radioactive decay of nuclei. They're the force, if you think about it, everything in a nucleus is positive or neutral. There's no electrons in the nucleus. All right? So if you have a ball of positive protons, What's holding them together? You know? Why don't they just repel apart? And why are there even nuclei at all? You know, what holds neutrons in there? You know, neutrons, they don't have any attraction or repulsion or anything. They don't have jack. But yet nuclei can be very stable. All right? And so what we found, but we figured that some nuclei, you know, like radium, uranium and stuff, are unstable. They'll fission, they'll split spontaneously, and we could force them to split. That's what a nuclear reactor does. And a nuclear explosive, you know, force an uncontrolled chain reaction. But anyways, so there's two forces in the nucleus. One of them holding the nucleus together, and another one holding protons and neutrons in kind of a resonance that mediates a decay of a proton into a neutron and an electron. An electron going backwards in time. What? Did I say backwards in time? Yeah. An antimatter particle known as the positron, the antimatter match of the electron, we model it quantum mechanically as an electron going backwards in time. I'll show you that at probably the very last day of class. But the point is that there's two forces in the nucleus. The weak nuclear force that mediates protons and neutrons decaying, and then the strong nuclear force that keeps the entire ball of the nucleus together. So those two forces, weak nuclear force, strong nuclear force, gravitation, and electromagnetism. But now we have a theory that unites electromagnetism and the weak nuclear force. It's called electroweak. Now your grandchildren will probably think of, you know, the stuff we're talking about now as electroweak theory. You know, it's just in the last 20 years, 30 years of stuff that we've, you know, got a real good experimental hold on why the weak nuclear force is actually the big brother of the electromagnetic force. But the first guy to do it was right there, Michael Faraday. And hopefully we'll get the strong nuclear force joined up to the electroweak, and then we'll have three forces of nature unified. And hopefully somebody in this room will be alive with the day that they unify gravity with the other three. And that's a tougher problem. So what we're talking about today is electromagnetism. Now, here's your lab schedule. I got this from the lab supervisor. You guys are up here somewhere, I guess, right in this row number 5, Kirchoff's laws. And then you got, now look at this, charging and discharging RC circuits. Ding, you already know how to do that. Exponential decay. So you're going to be doing that stuff next week, I guess. And then magnetic field of a permanent magnet, current carrying wire. So we've already talked about this stuff. And then eventually you're going to be down here in Faraday's law and resonant frequency of LRC or LCR circuits. These are the topics that we're going to start talking about Faraday's law today, and then LCR circuits probably Monday. So that's kind of where. So we're actually lecturing a little bit ahead of lab for once. Couldn't happen to a nicer set of students. All right. So our main topic for today: magnets and flux. The answer for the question? Oh, D? Capital D? For what question? What? Say it again. Somebody was talking over you. Oh, what's the question? I'm giving you the answer right now. The answer is, yeah, we can do it. Michael Faraday, yeah, and the answer is yes. And Michael Faraday blazed the trail. Now we're following in his footsteps. He's been to the top of the mountain, so now I'm going to guide you along in his footsteps. Now, we've already talked about the magnetic field. Okay, good. You know, we're not experts, but we got a little familiarity with it. Circuits, Ohm's law, we got a little bit of know-how there. EMF, we got a little bit of know-how there. We're not experts yet. We're not electrical engineers yet, but hopefully those days are never going to appear. But the new stuff that we want to talk about is flux. And this is, so we're not talking about the flux capacitor, which is the key to time travel, but the flux in the context of magnetic fields and circuits, it's a combination of information about the magnetic field and information about the circuit, physical information, you know, like the breadth of the circuit, you know, how much current is in the circuit, stuff like that. So field lines represent, as you know, they represent, for magnetic fields and electric fields, they represent the strength and the direction of the field. Now, we're going to be working directions here, and guess what? There's another right-hand rule in your future in a few minutes. We're going to do a little document camera work in a few minutes, and there's another right-hand rule that, you know, is pretty easy to actually use. But and then the circuit, you know, the circuit occupies space. So the physical parameters of the circuit, you know, like its area, you know, if it's a loop, you know, the area of the loop, all right? And then the strength of the magnetic field and its direction, you know, so we all have a fairly good handle on all that stuff. All that goes into putting together the flux. And we'll do a flux calculation on the document camera. So it's pretty basic, but it can get really tricky. Now, Faraday's key concept, this is his discovery. You know, his question was, can you produce electricity from ordinary magnetism? And he discovered the answer is yes. And his key concept, or as we call it, Faraday's law, comes in two different forms. The key concept is there relative motion between the magnet and the circuit? And definitely use the word relative in your notes. And when I use the word relative, I'm always thinking relativity, the theory of relativity. And yes, my wonderful students, the conceptual linkage between Michael Faraday and Albert Einstein is one step. First Faraday and then Einstein. And Einstein brought it all the way home. So yeah, relativity, relative motion. The other version of his key concept is that the flux has to be changing over time. Now, so what I'm going to do is show you how to calculate flux. Okay, but first we're going to talk about and look at pictures, diagrams from the textbook about the relativity of motion of magnet and circuit. All right. So let's take a look at this idea. And this is, I think it's like the very first diagram in the chapter. Okay, it's this one. This is from chapter 22, section 1. So this is a set of three diagrams, and I'm going to look at each one in turn. So let's take a look at this one. If the magnet and the circuit are at rest relative to each other, no juice in the ammeter. The ammeter that's our word for the meter that measures amps, the meter that measures current. So they're just kind of sitting there on the desk. There's no relative motion. You know, the coil's not moving to the left, and the magnet's not moving to the right. They're both at rest with respect to each other. Zip, zap for current. All right? Now, here's a variation that does produce current. And this is the middle picture of that figure in the book. If the magnet, for instance, the north pole of the magnet, by the way, the field lines of a magnet go out of the north, then they loop around, and they end at the S. So they go from N to S. And by the way, this would be a good multiple choice question for the test. And I don't have it on a clicker, but I'll just ask you a question. If you put that bar magnet there in the diagram, if you hung it by a thread, a long thread, and so it was balanced and level, and then hung the thread from the ceiling or from a rack of some kind, so like maybe about 1.5 foot of thread supporting the bar magnet, which end would go towards Santa's workshop at the North Pole? Which end? The N or the S? No. The N is they call it the N because that's it's after what compass needles are. So that's the end of the compass needle that would point towards the north, towards Santa's workshop. Okay? So now you got to ask yourself, now the magnetic pole of the Earth is it's a few degrees away from the actual North Pole, where Santa's workshop is. In other words, the North Pole of the axis of rotation pole. So they're a little bit off, but. So you have to ask, so the N pole points north. So what kind of pole is that up there in Canada? Yeah, but Canada's not in the southern hemisphere. So how can it be south? It's north of us. Geographic North Pole is the place in the Arctic Ocean where the Earth, the spin axis of the Earth, comes in there and it comes out in Antarctica. And if you stand on the north geographic pole of the Earth and look up, you'll be looking straight at the North Star, and everywhere else that you look is south. All right? Yeah, so the N pole of this bar magnet points towards Canada. So now I'm not going to give you the answer. I'll just let you think about it. And maybe on the exam, hopefully you'll have an answer for it. Anyway, the other variation of what Michael Faraday found was, let's go back to this one. If the magnet approaches, the more field lines are poking through those coils, because these field lines out here are fairly spread out, but these field lines in here are fairly compressed together, so that's a stronger field. Okay? So the strength of the magnetic field is increasing in the region of the coils. All right? And when you notice that there's a motion arrow here. There's your velocity. So you would say that the relative motion is that the coil and the magnet are approaching each other. And in fact, it's this guy holding the bar magnet approaching the coil. All right? But it could be the coil going towards the magnet. The magnet's on the desk and you move the coil. And if you do that, then you'll get the same effect here. Right. Now the other way to get current, but notice the minus sign up there in the ammeter. See this? Look at the ammeter up there. 100, what does it say? 120, okay? 120 milliamps or whatever it is. All right? And that's for north field lines poking through from the left to right. All right? Now, here's north field lines leaving from right to left. See the arrow there? The relative motion of the magnetic field and that generates the current in the opposite direction. Now there's a right-hand rule in all this that's related to the shape of the coil and the direction of the current. Okay, and we're going to do, so get your right-hand rule ready. All right. But let's look at the actual calculation of the flux. Basically, the flux is a product of two quantities. The magnetic field strength, B, and the area of the surface that the coil of wire spans. Okay, so it's a coil, it's a circle, right, like this. And so if you think about it as, like a piece of tissue paper that goes, that's glued to the coil, that surface, and then the number of magnetic field lines poking through the surface, that's the flux. So the strength of the field times the area of the circuit, of that surface of the circuit. And here's a nice diagram to show that. So you look at the plane of the circuit loop, and you make a surface. You decide on an up or a down orientation of the surface, okay? Or if it's like this diagram, left or right, okay? And then how many field lines pierce that loop? So basically what you do is, you calculate B times the area, and it's pretty simple. Excuse me. It's pretty simple to do that if the magnetic field is straight in. So if the magnetic field is perpendicular to the surface, it's real easy. In this case, you would then say that upward, or in this case, rightward piercing field lines means that you have positive flux. All right? And you can choose the other direction to be positive. It's not a problem. But if I decide that my rightward piercing field lines are positive flux, then leftward piercing, or downward, would be negative flux. All right? Now, I've only got rightward piercing, but the thing is, this one, it shows more positive rightward flux from rightward poking field lines in part A, in image A. That's this one up here at the top. And then image B, it's still got a little bit of rightward poking field lines, but not as many. Okay? So your bar magnet's a little bit further off to the left, for instance. Okay? So you have you have positive flux in the lower image, B, but it's not as big of a number. All right? So the change in the flux, delta flux, is negative. And that, my wonderful students, is significant. The SIGN of the flux change over time is really the best way to describe Michael Faraday's law. And this is figure 22.12. All right. Now, another thing, and this is kind of this one, figure 2212, is kind of idealized. You have a nice flat, it's even a rectangular surface, and you can actually visually count the field lines. The way they've got them drawn up there. And you know that the bar magnet or whatever your horseshoe magnet is a little bit closer to the top surface than in the bottom image. All right, so it's really idealized. But now here's another variation that you have to also take into account, and that's the relative orientation of the surface and the B field. Now, in the first image here, on the left, your coil, you're looking at it edge on. All right, so you don't see the surface. The surface is oriented like this. All right, it's like slicing into the plane of the screen. All right? But if that's the case, then the magnetic field lines are poking straight through. Now so this is like a coil between the poles of a horseshoe magnet. A horseshoe magnet has nice uniform fields, and these ones are pointing downward. Okay? And the angle is 0 degrees. All right? Yeah, that's... And you might say to yourself, what's 0 degrees? This normal, this is what they call the normal vector here, this dashed line. I'll do the exact description of the normal vector on Document Cam. Here's another picture. What if you spin the coil a little bit counterclockwise, 60 degrees? Well, your normal is still perpendicular to the surface, but it's 60 degrees, and it makes, if you think about it, it makes an angle to the field lines. So there's sines and cosines of 60 in this. All right, so you might have to do a little bit of trig. All right. And you can see that you're not catching nearly as many field lines. As a matter of fact, in this configuration over here, let's see, 1, 2, 3, 4, 5, 6, 7, 8. So you're catching a flux of 8 field lines, all right, in this surface. But over here, I don't know, what are you getting? You're getting 1, 2, 3. You're just getting 3. All right? And then over here on the far right, now your coil is turned this way. So the spin axis for this coil is like this. All right? The initial configuration, the surface of the coil is flat like this. Then it spins to about 60 degrees like this. And then in the third picture, it's straight up. And in that particular situation, you have exactly 0 field lines poking through, because the field lines are going parallel to the surface, so there's no poke through. Right? That means there's no flux. So, so that's the idea of flux. And if this loop were spinning, if you had, if you were spinning this loop, if it was just like a loop of wire on an axle and you were spinning it like this, or if you had a hydroelectric dam with a bunch of turbines spinning that loop like this, you would be producing alternating current in the wire. It's pretty nice. So now let's get to the nitty-gritty of how do you produce current. EMF produces current. If you have a battery, good. If you don't have a battery, but you have changing flux, yeah, you're good. All right? And this is the Faraday's law, that the EMF generated by changing flux, whether it's the magnetic field or the loop changing, it generates flux, a change in flux per unit time. And then capital N here is the number of coils. All right, so if you have circular coils, the area is pi r squared. And if you have 10 of them, then your total area is 10 pi r squared. And that goes in the numerator. And then your change in the magnet, and then your trig comes in, with the cosines. If you're spinning it like this, you get, cosine of 60, sine of 60, all that stuff comes in the numerator. And if you're spinning that coil at a certain angular rate, that angular rate also comes in with the delta t. So the cosine will change at a certain rate depending on how fast you spin it. And all that's encoded in this thing. And so what we're going to do is do some simple examples of this in the document camera. All right, so, but look at that equation. There's a minus sign there I didn't talk about. What does a minus sign mean in terms of an EMF, in terms of a voltage? You know? What does a negative EMF mean? Well, my wonderful students, the EMF means that you have to use a right-hand rule. The minus sign in the EMF equation means you have to use a right-hand rule for this surface, the surface of your coil. And we're going to work that out, and I'm going to show you how to get a handle of the minus sign and everything after the break. So let's take a 10-minute break, come back 10 minutes. If you want to get your homework, come on up to the front. And I'll pause the YouTube. Okay, you're dismissed, and homework in WileyPlus.com available by lunchtime on Friday, if not sooner.